embedded systems testing. How can we simplify such a thing? So why do we want to simplify embedded system testing, and what is the problem? Why are we doing what we're doing with respect to testing? We want to bring the unit test, the integration test, and the system test as close as possible to the implementation. So we want to test earlier and we want to learn earlier. So system and integration test as close as possible to the implementation. Another point of view is the development cycle. So what are we doing when we're developing an embedded system, and where are we testing? So from left to the right, you see the typical development process for an embedded system. And usually you start on an evaluation board, you start to develop your drivers, you configure your drivers, you create hardware-related software components, such as motor controllers, battery controllers, bus system protocols, low-level bus system protocols, and so on. On top, you create software components, and you integrate everything to an application. And eventually, you will have the real hardware, so the real ECU, the real control unit, and you integrate it together with the application software, and you start to test. So usually the points where you test are the unit tests for the software components. Later in the process, usually there is a HIL system test or a real system test. So a HIL system test, a simulated system test, or a real system test. You sit in the car, you get in the car and you drive around the block. This would be a real system test. The problem is that in the early phases, or while you're developing your software, usually do not have any equipment to test the rest of the application included in the evaluation board or in the microcontroller system. So what we do with the miniHIL, we bring the hardware in the loop test to the desktop of the developer. So we enable the early testing of your embedded system. So what do we really want and need? First thing is you want to test what is changed most frequently, and that's your software. You will not change your hardware every day 10 times or 100 times, but with the software, it's very likely that you will change it at least several times a day. If you have a bigger team, maybe 100 times a day. So that's what you really need to test very fast and very often. You want to test for every code change of every developer within minutes instead of weeks. You need a full regression test also for unrelated code. You know, the situation, you change something here and you on one side of your system, and on the other side of your system an error occurs and you don't know why. So you need a full regression test because there are dependencies in your system. You need a full test automation to enforce tests. So for example, a continuous integration that really executes every change, or for every change a test. And you need an automated hardware in the loop test because you want to test more than pure software units. If you only have software units, then it's better to use a unit test tool, much cheaper, much faster, much less effort. But if you have a hardware, if you have hardware attached to your system, so a microcontroller and an ECU, you need, eventually you will need a hardware in the loop test. So why is it so hard to automate tests for embedded systems? Let me give you an example of a customer project. It's a motor control system for an oil pump. It's safety critical, so we need to test the temperature shutdown for all values, or all border values for 300 relevant system states. So that's safety critical, so we need to test this. The customer had before a test system with a climate chamber, very big system. He put in the complete ECU with all the power electronics, with the motor, with the pump, with the hydraulic system. And the test stand was scripted with test scripts and test cases running on scripts. And the problem was that even if the automation would have worked for a long time, the tests would have taken something like 30 days. And so it never happens. And it was not automated very good. So once in a while you had to fill in hydraulic liquid, or the system failed, or whatever. So it was really hard to run the test automation for a longer time. So it's very hard to automate such a test. But if you only want to know whether the integration of your software in the microcontroller with all the electric functionality works again, it's easier to take out the microcontroller with the complete software and the drivers and simulate the complete environment. So you simulate the electronics, you simulate the motor, the pump system, the hydraulics, and now you can bring the software on your microcontroller in any state you want to test. You can do failure injection, you can completely automate the system, because it's only a simulated system that surrounds your microcontroller. And this test took about 50 minutes for all states. So this has been done on every commit. So that brings a very high level of quality to your system development. And also it speeds up the development process. That's a very important thing. So let's have a closer look at the system, what it contains, and what kind of tests you run on which level. So let's start with the pure software units. Usually you have a unit test, or it's possible to test a software unit, a single C module, or a class with a unit test tool. That's the smallest unit usually you test. Then if you take a couple of units together, you can run a software integration test. That's something you also can run on a unit test platform. So it's pure software test. So it's easy to do, it's cheap, it's fast. So please do that. So the next level is a bit harder to do. If you want to integrate the drivers and test the complete software integrated in the microcontroller, you need something like a miniHIL, like a hardware in the loop test. So the hardware software integration test on the microcontroller level, that's the smallest possible hardware in the loop test. It's hardware in the loop because you really test on the electrical level, on the pins, you stimulate the pins, and you verify also on pin level, on signal level, whether your application works or not. That's where the miniHIL is focusing on. Then let's get a little bit bigger. Now we want to test the ECU, the complete ECU, including the power electronics, the sensors, the actuators, and so on. Now you need a big hardware in the loop test stand, possibly with power electronics and so on. And that's already much bigger, much slower, and it's far away from the software. So it's not so easy to test your complete software stack there. And in the end, you want to run a real system test. So you really take your system as it is, and you try it out. Yeah? You sit in the car and drive around the block or through the desert or something like that. Let's have a look at the frequency and so on. So the unit test is the fastest thing you can do, and so you can do it every time you change something, and it's really inexpensive. So a unit test is much cheaper usually than a hardware in the loop test, and so you can run it fast, often, and cheap. And the further you go down, the bigger your system gets. You want to test, the slower your tests get, the less frequently you test them, and the more expensive the tests get. So the miniHIL is here right in the middle. It's the, let's say, it's as fast as a unit test, but it's not so hard to do like a big hardware in the loop or a system test. So it's much faster than that. Let's have a look at the typical response time for the test levels. A component test, unit test, for example, or a system software integration test would be a component test. Usually needs a couple of minutes to run. So you can run this easily on every commit or in every code change. The next step is an integration test. Usually integration test is not done, or at least the hardware software integration test is not done in most development phases. And the next step is the system test. System test, from what we know from our customers, is running between 2 and 12 weeks. So every 2 weeks, 4 weeks, 10 weeks, a system test is executed, not because it's running so 12 weeks, but because it's really expensive to do that. And it takes a lot of resources and expensive systems to do that. Acceptance test is on system test level, so it's also running in the same frequency usually. So what we do is now we bring the hardware software integration test in form of miniHIL to the developer's desktop. And this test can run every 5 minutes if you want. So on every commit, on every code change, you can run this. So it's as fast as a unit test, but it's already a hardware in the loop test. So fast turnaround, and by having that with an inexpensive hardware, we're really closing the testing gap here. Let's have a closer look at the hardware. Let's start with the hardware setup of a miniHIL board. The blue board here is the miniHIL. We have adapters for microcontrollers. In this case, it's a standard evaluation board of STM32, Cortex M4. In this case, it's a pump control. And what we are testing now is the system under test is the software on this microcontroller. So we test the software on the microcontroller at the pins of the microcontroller. So typical things are PWMs, SPI, I2C, analog, digital, and so on. So now we connect the pins of this microcontroller over this patch panel with either directly the pins of our test system or indirectly with the I/O extenders of our test system. So now we have an electrical connection to all the signals in both directions we need to really stimulate and monitor the system under test. So now what we need on this side, on the test system side, are two things. We need, first of all, we need test cases to really test whether my system works or not. But the problem is, it's not that easy like, for example, in a unit test, because you need an environment simulation. Because if you do not have a motor attached to the system, you will never get to the point or to the state where you actually can test your system. So you need to attach a motor. If you don't have a motor, in our case, we don't attach a motor. So we need to attach a simulation, a motor simulation. And that's exactly what we do. We simulate all the components as open or closed loop simulations, which allows us to bring the system to any state where we want to test something. Another aspect here is if you have this simulated environment, for example, a simulated motor, you can make a lot of different failure injections. So basically you can break the motor in any way you want because it's only a simulated motor. You can break a cable, you can whatever, introduce any kind of failure injection here. Okay, so now we have a hardware platform where we actually can connect the I/Os of a microcontroller to a test system. Now we need to model the environment simulation and we need to model the test cases. For that, we have a development environment, model-based development environment. It's a component-based method where we can model the structure and the behavior for the test system. So this includes the environment simulation, motor simulation, battery simulation, whatever simulation you need. And this also includes the test cases. Also, the test cases are modeled, and from the complete model, we generate C code. We compile the code, we flash it to the miniHIL board, and now the miniHIL or the image is running directly on the miniHIL board because it needs to be hard real time. For example, to simulate the motor control, you need frequencies between 10 and 30 kilohertz. And of course, we can do that. If we couldn't do that, we could not simulate the environment for a motor control. Yeah. And now the test cases and the simulation is executed, and the test reports are logged via USB back to your development PC or also to the continuous integration server. Then we transform the logs into diagrams, and the diagrams give you the right view for the right problem. So what failed, or which feature coverage or requirement coverage do I have achieved, and so on and so on. And then you learn and iterate. Either you change the system under test or the test system. Let's have a look at something special we have in the models. We also can provide combinatorial state transition tests. The idea is you model the external, the expected behavior of your system as a state transition diagram with all the variations your system can take, all the different paths your system can take. So it's a very, very compact way to describe combinations for paths and for data. And from there, we generate not only this diagram, but also for every path here, we generate the test case. So in this case, from the diagram on the left side, we generate all the 15 test cases necessary to cover this diagram, to really cover the test cases I need to test the expected system behavior here. And if you go higher with a metric, you can as well generate thousands or 100,000 of test cases, depending on what you want to test. In some systems, it's very useful. In some systems, you don't need so many test cases. But you save a lot of work by doing that. But that's only the second or the third step. First, you should test your requirements. So what does a miniHIL workplace look like? On your desktop, you have, for example, a laptop attached to the miniHIL board. And that's the usual setup for one project or one developer, or also for the test developer that actually develops the test cases and implements the test cases. And but if you have bigger projects, more developers, or more than one project, at a certain point, it's very nice to have this test system running on a continuous integration server. It's also possible, so you can hook up the miniHIL to a continuous integration server, and then every code change triggers the continuous integration build, the test, and the delivery potentially. I always say, please also deliver your software continuously, even if you don't need to deliver it. So you know always that you can deliver it. That's also kind of test. And here you see a typical setup for a continuous integration server in a rack. That's about 1 meter high, eight miniHILs for 8 different projects. So whenever you change a line of code, the continuous integration server tests the line of code or the change on those miniHIL boards. So in this case, this would be a setup for 8 different projects. It's a very small setup for 8 projects. So by doing that, every code change of every developer for every project is tested within minutes. Of course, he needs to make a commit so that the Git repository or Subversion or whatever you use knows that something has changed. But on every commit, all the tests are executed. So feedback time is a couple of minutes here. So now let's have a little demo. I want to show you what the development environment and such a test setup looks like. My test system or my demo system has, as a system under test, STM32 microcontroller. I'm showing you the system in real life here. Here's on my desktop. That's the system under test, STM32 Cortex M4. Here, the test system, I connected all those IOs between the, or made connections between the system under test and the test system. And here you see the system under test. That's the Cortex M4. It runs a microcontroller with a motor control software for a BLDC motor. It generates 3 PWMs, block commuted with block commutation. Then we run the simulation, the motor plant simulation, and the simulation generates 3 Hall signals as digital signals. So the motor really runs in closed loop simulation together with the plant simulation. And then we simulate the temperature sensor as an analog output. On the other side, we have an analog input that measures the temperature. And we have a UART sender and receiver to control the speed of the system under test and so on. So now let's have a look at the electrical level. I recorded with a Saleh logger with a logic analyzer on the electrical level what such a test case looks like. Here you see a more fine-grained monitoring. That's the block commutation of the BLDC motor of the 3 PWMs. They go into our simulation. The simulation calculates the speed and generates the 3 Hall signals so that the motor controller can really run. And here we have the UART with a change, for example, for a speed. And here you see a bit more coarse-grained. Also, again, the PWMs, the Hall signals, the UART. And here you see the simulated temperature. That's an analog output, 0 to 3.3 volt, where we simulate the temperature sensor. And that's just an analog output of the simulation of the test board, because we want to monitor the speed in the model of the simulation, so that we can make a correlation between the simulation and the system under test. So let's have a look at some test cases. For example, one test case would be we change the speed over UART. We change the speed. The model reduces the speed. The system under test reduces the speed, so the model also reduces the speed. And here you see the speed is getting lower. The frequency is getting lower. Next test case would be we have a temperature error. The temperature is too low, so the motor needs to shut down. You can see the PWMs are really at 0. That's, for example, a test case with I want to measure whether the PWM is after a temperature error, after, I don't know, 10 or 50 microseconds that it's at 0 for a certain time. Then the motor starts again. Then we have the temperature warning as a typical error. So that's a limp home functionality. So when the temperature is not critical, but it's a bit too high, a bit too low, we have a limp home functionality we can test here. And that would be a recovery after an error shutdown here. So those are just examples what you can do, for example, with a motor control. Now, to test the motor control. Now let's have a look at the development environment. I'm opening the Eclipse development environment. Our modeling tools are Eclipse plugins, so we plug it into the Eclipse platform here. And I'm going to show you the software, how we develop the software. So this block here, that's a component. It's called an actor in this method. And everything inside this actor is generated and compiled and is running on the test system, because we're developing the test system now. I double click, so I go inside my example here. That's a component where my test case and the simulation lives. Down here, we have all the IOs we need to connect with the system under test. So we have analog adapters, for example, for the temperature sensor, a digital out adapter, UART, a Hall generator, and a duty capture unit. So those are the IOs. On the next level, we have the simulations, for example, the motor temperature. So in the test case, I can say, for example, the motor temperature should be 10 degrees centigrade. And here it's converted to an analog output. And in the end, the pin, the output 1, that's here, this cable, goes to, for example, 1.2 volt or something like that. Same with UART. And here we have the duty capture unit. We measure the 3 PWMs. When the 3 PWMs are measured, so after every cycle, we send it to the motor simulation, and the motor simulation calculates the frequency of the motor new, and over this whole GAN out output, we set the new speed for the whole generator that generates the 3 digital outputs to perform as 3 whole sensors. So now we need, for the simulation, we need a behavior, because right now we're only seeing the structure of the test system. So let's open the behavior of this block, of this actor. That's a state machine. It's completely modeled. So when a PWM comes in, a new measurement, a new duty cycle, we remember we store the duty cycle in a member variable. Then we calculate the speed. Oh, that's just a piece of code here. This also could be a part of a Simulink model, a generated code of a Simulink model. If you already have the motor model, you do not have to redo it again. And here we send the new speed to the whole generator. So whole out. I could change the speed now. I could change the direction the motor is running. This would be, for example, failure injection, because you do not expect the motor to change at full speed the direction or something like that. So you can introduce any kind of error here, because you have 100% control over the model and over the IOs. So now the whole generator is generating the signals, and now you can run your motor controller completely against the simulation and bring it to any situation where you want to be. So the last block I have here is the test case. The test cases, you could model them as well as state machine, but it's not very efficient, because if you know it's a test case, we have a more efficient language. It's again a behavior of this block. And now I'm inside the test case. Again, the test case over the ports. So the interfaces here are called ports. So it's a UART port, a motor simulation port, temperature port, and so on. And over the ports, we can access directly the system under test or parts of the simulation, depending what you want to modify. For example, here I want to have a step where we check the speed. So I get I send a signal to the motor that I want to measure the actual speed, and the motor answers where the motor simulation answers with a measurement of the actual speed, and we control whether it's in the right range or not. So I could also, for example, simulate the temperature now. So set temperature, that's in degrees centigrade. So I would set the analog output to a value that for the value needed for 4 degrees centigrade. If you change something here, you see on the right side, you get automatically generated diagram that tells you in a graphical way what you did in the textual model here. For the smaller steps, that's not so useful, but the step is the basic step, a test atom, where we define actions and reactions that should be reusable, because now on a higher level we want to define sequences, and in a sequence we combine various steps to bigger and bigger test cases. So it's hierarchically. And in the end, we make test suites. In a test suite, for example, it's a test suite for a demo motor component test. So those are all the test cases now needed to test the motor control. So that's the way we model the test cases. One last thing I want to show you is the state transition graph here. That's this combinatorial test case. Whatever I change here changes the test model here. And now I generate much more test cases because I added a lot different paths. But that's very efficient, but that's usually not the first step you do. First step you do is you make a smoke test, you start up your system, you let the motor run, you let the battery run, and so on. And then you start to introduce errors. And when you want to go really deep, you use the combinatorial tests, for example, for a long-running stability test or a performance test or robustness test or something like that. Okay, so that's how you develop the test cases. Now let's run something. I have a graphical user interface here opened to connect directly with my miniHIL board. So I'm connecting directly with the board. And so I can control the board here from this panel. But the interesting thing is are the test cases. Those are the generated test cases on the miniHIL now. So now let's assume we changed the software here on your system under test, and I want to run the test. So to simulate an error, to introduce an error, I will just pull a cable here. Now I'm going to run the test. And while the test runs, I'm pulling a cable here. So now we have an error. I put it back in. So now the error is fixed. So let's assume this was a software error. Now you want to know exactly what happened here. We see that's demo integration test. The motor control speed failed. So let's have a look at the log of the system. Test system. So those are the traces. Motor demo integration test. I open this with a regular browser. It's just a file you can open on the file system with a browser. And here you see exactly the place where the test case failed. I click it, and in my IDE, the place where the problem occurred is directly shown. So request speed, that's exactly request speed. That's the step where it happened. So UART sent done. That's the last thing we heard from the target, but we would have expected a reply over the UART. Of course, it did not reply because I pulled the cable. So that's how you work on a desktop. You can build, of course, the new test models. You can build and flash them from here. And now, for me, the most interesting thing for bigger projects or for, let's say, projects with more complexity, more developers, very frequent changes and so on, it's very nice to have a complete continuous integration. And that's the last thing I want to show you. So the board is hooked up to a continuous integration server. Continuous integration server, it's a Jenkins server that runs locally here. And I also have a Git repository locally here on my laptop. So now I'm going to change the system under test. So before I've changed the test system, now I'm going to change the system under test. I'm going to change a value of the duty cycle. I fix it to 20%. So the motor is running all the time with a constant speed. That, of course, that doesn't make sense. So it's supposed to be a bug. Now I'm going to commit this as a Git commit here. Let's call this bug. I commit it, and now goes to the Git repository, and let's have a look at the Jenkins server. So at the Jenkins server, it's on standby, and whenever it detects a commit, so now the commit is still running, so now it's done. So when it detects a commit, it immediately starts the build. So now it's checking out the changes in Git repository. It assembles the project, so it generates the code for the models. It compiles the code, not only the test system, but also the system under test. Now it's flashed. So let's have a look here. Here you've seen it stopped blinking. Now it starts blinking again. So both systems, test system and system under test, have been flashed, and now the tests are running. So So yeah, we can have a look at them while I'm running. That's not very interesting. That's very much better to see in a graphical diagram. So let's have a look what happened. It's yellow, so something failed. Here I see the test cases that actually failed. And now let's have a look at the traces. And here you see the problem. And that's on the server now. And if I click on the server diagram on expect failed, and I have the right IDE open with the right project, then I get directly to the place where my system actually failed. And now it's up to you as developer to find out why your system failed. Yeah? But that's as close as you can get with a test system. And yeah, so let's have a look at some of the diagrams. So the feature coverage also tells you the temperature limit has failed, the motor control has set speed, and the brake has failed. Yeah, because I changed the duty cycle, so expect something to happen here. And last but not least, you also get generated documentation for the tests, for the test specification, and also for the test execution. Here in this case, you see the combinatorial test. You see all the graphical specifications for the textual models you made. That's better to understand if you want to discuss this in your team or document this for safety requirements and so on. Okay, so that's it so far from my side. If you have any questions, please don't hesitate. You can put them in the chat, or also afterwards you can ask us directly via email. And so thanks for your attention. Just want to mention, if you have any questions, you can also directly contact Michael Weiss from Hitex. Hitex is doing a lot of projects and helping their customers with the miniHIL.